All right. Now, the idea of a hybrid anything is usually where we take two things that may not be related or some things that may slightly be related and merge them to form a new organism or a new method. In my mind, that usually keeps coming to mind is the hybrid cars, where they run on gasoline as well as electricity, or there are different plants, many fruits that people enjoy that are actually hybrids. And so we want to look at how that relates to the actual bonding. Now, a hybrid orbital is simply mixing two orbitals together to form a new orbital. Makes perfect sense, shouldn't be too bad. Now, we need the concept of hybrid orbitals to explain molecular shapes. Why? Because when we look at atomic orbitals, we notice that we're actually going to end up with some different energy levels between them. A p orbital is higher in energy than would be an s orbital. But when we look at the shape of carbon and say methane, it actually has 4 equal bonds. We don't have one bond that's weaker than the others. So the way that this is actually accomplished is by using orbitals. We'll try to keep it as simple as possible to make sure that it makes sense. Now, when you mix n orbitals, we must get n hybrid orbitals. That makes sense depending on the number of orbitals that we actually mix and put together. That'll be how many hybrid orbitals. The other orbitals, if they're not used, they just remain there. So, example, if we mix one s orbital with 3 p orbitals, we'll get 4 sp3 orbitals. So hopefully this is going to make pretty much sense. sp3 hybrid orbitals that have the same energy. Now, our hybrid orbitals, and just a couple of examples, and some of these are things that we've just talked about. But going back to geometry, if we have an sp orbital or two sp orbitals, we have two regions, and we hit an s and a p orbital and merge them, or we'll end up with an s with 2 p orbitals, we get 3 sp2 orbitals, or continuing on the rest of the way, 4 sp3, and it continues to go on down the line. So you want to pay attention to how they're connected, what those geometric shapes are, and how that's going to play out in terms of their hybridized orbitals. Now, the number of electron domains on the atom will indicate the hybridization needed. So again, look at what it's connected to. Look at how many lone pairs are actually there. That's going to help you to determine which of the orbitals are used, how many hybridized orbitals there will be. Quick example, if we're looking at CH2 with a double bond, or ethylene, each carbon has 3 electron domains, so its hybridization must be sp2 with 3 hybrid orbitals as well. And so that's what you're seeing for each individual carbon. Now, in terms of the bonds that we've talked about, we break it down even a little bit further, and we look at sigma and pi bonds. Now, overlapping orbitals can come in two main varieties. The first are going to be sigma bonds. That's what that symbol there is. It's a lowercase sigma in Greek. And these are, the electron density lies on the axis between the nuclei. What does that mean? We're actually going to have a direct connection between these, between the orbitals of these molecules or these atoms. Now, all single bonds are going to be sigma bonds. So this is an easy thing to remember. Once you've drawn the Lewis structure, you can determine which of them are actually going to be your sigma, your single bonds, and which will be your pi bonds. So, going back to what I was saying, each of the sigma bonds, you notice they're all within this plane that's given to you. They're not sticking up, they're not sticking down, but they're all just within the plane. And it also even gives you the hybridization of each of those connections. Now, to go on a little bit further, pi bonds, we should recognize the pi symbol. Now, pi electron density lies above and below the plane of the nuclei. So those things that we just saw sticking up throughout the molecule, those were our regions where our pi bonds will usually be. And we're actually going to end up with a connection as you see through these. Now, will they actually be connected? No, but it's just the attraction of the electrons and the space that they will share will allow us to have what seems like a complete bond between them. So if you're looking here, you're seeing that connection there as well as beneath. All double bonds consist of one sigma bond as well as one pi bond. So you want to keep that in mind. If you see a double bond, that means one sigma, and one pi bond. A triple bond would have then one sigma and two pi bonds, just based off of the geometry. And so you want to look at how they're going to be arranged around those central atoms. Now, often the p orbitals are involved in pi bonding. They're going to come from unhybridized orbitals. So you want to keep that as well in your mind. And this some major things we'll go to. A total of 5 pi bonds are formed when the overlapping of sp2 orbitals of carbon and the pi bond is formed from the unhybridized overlapping p orbital. And you'll see what we're talking about in just a second. So, if we're looking at this situation, this is actually formaldehyde, that we're dealing with. So, we have our carbon. Here you should notice it to the left of the screen. And it's going to form a sigma bond with each of the hydrogens as well as it's going to have one sigma bond with the oxygen. Now, in the process, because of the fact that it actually forms a double bond, you see that we have the connection here as well as the connection here. This is the region where we'll have one electron, and I'll draw by having an arrow going that way, and in this region we have the other electron. And so these are where those pairs of electrons will be shared between these two molecules. Between these two atoms. Carbon and hydrogen both have sp2 hybridization at this point. You look at what they have, what they're connected to, their regions of non-bonding as well as bonding domains. The reaction, or the pi bond, is actually happening above the plane as well as below the plane to make that double bond work and stick. If we're looking at the example of acetylene, you see that we have the 3 different p orbitals that are represented here, and you see the actual connections between them. We have the 2 at the top and the 2 here at the side, forming our triple bond along with our sigma bond right here in the middle. In this case, that means we're dealing with sp hybridization in order to make this happen for a triple bond with carbon. Now, when we look at these pi bonds, they have a tendency to be what we call delocalized. Again, delocalized just meaning that they're able to move. They're not stuck to a physical location. Simply put, if there are resonance structures for for the molecule, the pi bond is delocalized or smeared between the 2 resonance structures. That's why we want to draw both of them, because it's not just representing one, it has to be representative of all. Looking at benzene, this is why we usually draw it the way that we do, because it's the shifting of the electrons. We're going to end up moving those double bonds. So what they usually do is draw it as a circle inside, showing that those electrons have the ability to move freely. This is what you're actually seeing happening in terms of our benzene ring. We have our pi bonds that are located on the plane. These are all of our sigma bonds that we're dealing with between our carbons as well as our hydrogens. But now we have our p orbitals that are also there, sticking up above and below the plane. Because these electrons are going to be moving around, we end up with this double ring appearance above and beneath, because it's just showing that those electrons are constantly moving. Now, the next thing we have to look at is molecular orbitals. And this is going to be very similar to what we were doing with atomic orbitals, but now we actually have to pay attention to more than just one element. We want to look at, and this is going to help us to actually explain Why is it that some molecules in liquid state or otherwise that we would not normally assume actually have the ability to interact with a magnetic field? And this is going to be based off what we call MO theory, or molecular orbital theory. We're going to look at some examples of this in just a moment. Now, just the sorry, my words are coming out. Just as the electrons in the atoms are found in atomic orbitals, electrons in molecules are also found in molecular orbitals. And each one contains a maximum of 2 electrons and have definite energies, meaning it's going to increase in energy as we go up, and can be visualized with energy level diagrams. Now again, this has to be in reference to the entire molecule. So we're actually going to see the relationship between each individual atom, but then we have to apply it to the mass scale. So let's look at the formation of H2. Now, we have a 1s and a 1s orbital. Each hydrogen is going to end and start really in a 1s orbital. So we have to look at resulting 2 molecular orbitals, for H2. There's going to be a bonding as well as an anti-bonding. Now, if there's an area where there is electron density that is not participating in bonding, that of course will be our anti-bonding molecular orbital. Now, also, we have to pay attention to what type of bond is going to be there. And this is going to tell us which electron is behaving as the sigma as well as the pi bonds. What do I mean? If we're looking at a relationship between s orbitals, most likely we're going to have sigma molecular orbitals. Sigma bonding as well as sigma star, that star there, the asterisk, which tells us that it's going to be an anti-bonding. The bonding are going to be in lower energy than the anti-bonding. Now, while this is probably very confusing, stick with us and we're going to see if we can't make this happen, if we can't make it make any sense. Now, in terms of molecular orbital, we said we have both of them at a 1s orbital. If we are paying attention at at our molecular orbital here at the bottom, when these two bond together, we're actually going to end up with a lower energy. Now, in terms of our previous example, if we're still using hydrogen gas, once we make those connections, there are actually no other electrons that are there. So we wouldn't have to worry about really going into our anti-bonding. Why? Because there are no electrons to be there. Each hydrogen has only 1 electron. Now, but we take this and we can then apply it to a couple of other examples. What do I mean? Well, let's look at this. Energy level diagrams or molecular orbital diagrams show the energies of electrons within an orbital. So the total number of electrons are placed in a molecular orbital starting from the lowest. Remember, electrons are lazy, sigma 1s, and ending when you run out of electrons, wherever it is that you happen to run out of electrons. So, using the example of what we just dealt with for our hydrogen, we have each hydrogen on each side so we know what's donating to our system or to our molecule. Once we've donated, we notice they're going to start low and then work their way up. Once we've done that, we run out of electrons. Now, also, we have to make sure that we're noting that each of these electrons within this orbital, within this bonding orbital, also have what we remember calling opposite spins. So, that is going to be a key factor here. We cannot forget that when those electrons go in, they have to be of opposite spin. Now, look at another example for He2. Now, some of you are already saying in your head, that doesn't sound right. That's not possible. Each one has 2 valence electrons that it's donating. So we end up with what looks like each helium, donating an electron, and it fills the sigma 1s, and then they donate the other one to fill the non-bonding. This lets us know, this is sort of like a red flag that says we cannot have this situation. If we have two non-bonding or two anti-bonding electrons, that this is not going to be stable and it's not actually going to form. But if we had this empty, then it would be no problem. Then we'd be able to move on without too much of an issue. So in order to predict the stability of a molecule from a molecular orbital diagram, we have to go into what is called bond order. Now, we're going to save this part for the last and final video, then we can wrap all this up, and you guys will be set to go and ready for your test. We're going to talk about this tomorrow in class, so be ready. Have a great evening.